My name is Tel Menezes. I am a researcher at the Center Mark Block in Berlin and member of its computational social science team, which is led by my co-author Camille Roth. It is my great pleasure to present at this year's Sunbelt some of our work on semantic hypergraphs and their application to news analysis. Text in natural language is a crucial source of empirical data in our field. Automatic text understanding is a very hard problem, but even relatively simple statistical methods can help uncover patterns and reveal structures. Distributional methods have become very popular. For example, topic models such as LDA and word co-occurrence models. These ultimately rely on the statistical modeling of the likelihood of certain words appearing close to each other. Of course, natural language is much richer than what can be observed with such methods. We are still far from AI capable of a human-level understanding of natural language, but we believe that it is possible to take steps in that direction. Here, we propose a language representation model that we call semantic hypergraphs, and that facilitates the task of performing more sophisticated inferences about the contents of a text. Taking advantage of modern machine learning methods, we provide natural language with structure and annotate words with indicators of their function. This makes it then possible to define patterns of meaning that uncover relations that go beyond topics and their co-occurrence. We will see that such patterns lend themselves very well to the identification of actors. What they say to each other, what they claim about each other, in the context of which topics and under which conditions. The kind of structure we employ is that of the recursive ordered hypergraph, which we found capable of accommodating the various constructs found in natural language. Hypergraphs are a generalization of graphs. While graph links or edges connect two nodes, hyperedges connect an arbitrary number of nodes. In a recursive hypergraph, hyperedges themselves can participate as nodes in other hyperedges. Sentences are transformed into hyperedges, which can then also contain other hyperedges corresponding to various types of entities, which, as we will see, are characterized by a type system. We use the universal rule that the first element of any hyperedge plays the role of connector, specifying in which sense the following elements are gathered. We can imagine connectors as somewhat akin to functions. They map sets of parameters to outputs in a certain way. Following this analogy, we adopt a representation for hyperedges that resembles programming languages. For those familiar with Lisp, they are akin to S expressions. This will hopefully become more clear by discussing the 8 hyperedge types, which are the fundamental building blocks that can be combined to express anything that can be expressed in natural language, but in a more structured and explicit way. Words are extended with codes following a / separator. We refer to these annotated words as atoms. The capital letters indicate the type of the atom. For example, C is for concepts. Concepts correspond to simple noun words. But concepts can also be represented by non-atomic structures. Concepts is our first type. New concepts can be defined by applying modifiers to existing ones. For example, red shoes. Modifiers are another type. Builders are used to define new concepts by combining several existing ones. For example, capital of Germany. Predicates more or less correspond to verbs and are used to define relations. Relations express facts, statements, questions, and orders. Triggers are used to define specifications for relations. For example, when, how, or if something happens. Finally, conjunctions are used to define sequences of concepts or relations. A typical case here is meat and potatoes, which is in itself a new concept. This latter type provides us with a good opportunity to give an example of a simple but nevertheless useful inference task: conjunction resolution, or the decomposition of conjunction-based relations into simpler ones. Let us consider here three simple cases. The first case concerns conjunctions of concepts, such as in the sentence, Mary likes books and flowers. In this case, it generates one relation for each element. Mary likes books and Mary likes flowers. The second case concerns conjunctions of relations with explicit subjects. For example, Mary likes astronomy and Alice plays football. In this case, the claim is decomposed into two separate claims. The claim that Mary likes astronomy and the claim that Alice plays football. The third case makes the subject explicit in situations such as the sentence, Mary likes astronomy and plays football, inferring in this case that Mary is the subject in the second relation by retrieving it from the first relation, and inferring then that Mary plays football. Here are two real examples from our corpus of news headers, extracted from the World News section of Reddit between 2013 and 2017. We looked at the most frequent hyperhatch patterns in this dataset, and we found that some of the most frequent ones correspond to two specific categories of utterances that are of special interest for the social sciences, especially the study of public spaces. These are claims made by an actor about some topic and expressions of conflict of one actor against another over some topic. The example shown on top is that of a claim made by North Korea about itself, and the example shown at the bottom is of an expression of conflict originated by Germany and with Russia as a target. The deep structure of concepts can be used to identify topics at various levels of generality. Military engagement in Syria is a possible specific topic, but it also implies the more general topic of Syria. This sort of exploration is facilitated by semantic hypergraph structure. So we employ such patterns to automatically identify the actors, expressions of conflict between them, and the conflict topics. Here we show a conflict network on the topic of Syria. A simple alliance detection algorithm identified two factions, the red one corresponding to NATO actors, and the blue one to the Russian sphere of influence. Some of the actors were not assigned to any one of the factions, and in this case they are shown in gray. We can use such patterns to infer many different types of things of sociological interest. As another simple example, the gender and type of actors, female, male, group, or non-human entity. Here is a table with the top 5 actors in our dataset for each one of these categories. We can also see here the outcome of co-reference resolution, another common task aimed at inferring sets of symbols or more precisely symbolic representations that all refer to the same concept. Inferring, for example, that Barack Obama and President Obama refer to the same person, while Michelle Obama refers to a different one. This co-reference resolution task takes advantage of the implicit taxonomy created by the semantic hypergraph recursive definition of concepts, as well as of the network nature of hypergraphs. Semantic graph-based disambiguation has been extensively explored since the mid-2000s, and it fits our language representation model quite naturally. We have experimented with other corpora and found that this approach appears to be sufficiently general for ad hoc applications in news analysis. We released an open source Python library called GraphBrain, with which we hope to make methods centered around the semantic hypergraphs model, such as the ones discussed here, available for the research community to explore and expand on. We believe that semantic hypergraphs can be applied to many other language understanding tasks and to other research domains. We invite you to take a look at the project's website and get in touch if this interests you. Thank you very much for watching.